Okay guys, this is video number 4, Math6500 Fall 2014. This is just more review. It's again, since it's been so long since since you guys have taken 5500 from me, and actually I guess maybe a couple of you didn't even take 5500. So no, I guess just one, just Alice. So I thought it was really important that we go back and review some things. So what I'm doing is, some of the videos I've done in the past I like, some I don't like. If I like a video and I think it's well done, I'll use it again. And that's going to be the case in this situation. What I'll do is, once I explain some things to you, I will transition into this video, which I actually created about a year ago for the inference for the beta 1, which is the slope of our model. Keeping in mind that our model is beta 0 plus beta 1x, and of course these are the parameters, and we usually take beta 0 as the estimate, and we take beta 1 as the estimate, b1 as the estimate of beta 1, and b0 as the estimate of beta 0. Ultimately, our model looks like, plus the error term. So let's put our subscripts of I in here, because the only way that we can take data that's been collected in terms of x and y and actually create them to be equal is if we include the error term. So guys, put on your radar the differences in these two forms. Alright guys, so here's what's going to happen in this video. First of all, I'm going to go through an example with ACT and high school GPA. We're going to review how to find a test statistic for B1, how to calculate the p-value, and we're going to learn how to review, I should say, hopefully, maybe learn, who knows, how to construct confidence intervals. Keep in mind that some things in the video don't apply. I think I mentioned something about assignment number 3. You don't have an assignment yet, so just pay attention to the content and ignore anything that has clear reference to the class that that was offered in summer of 2013. So guys, enjoy, and put a little smiley face there. That guy's got one eye. That's kind of weird. So anyway, enjoy, and this is going to get ready to transition into the video that we'll use as review. Is our model is, as we know very well now, plus our error term. And guys, hope by now we know the beta 0 and beta 1 are parameters. X sub I is the constant, and of course E sub i's are our errors. And for our errors, we know that these things are independent. We don't want systematic errors. And they follow a normal distribution, mean 0, variance sigma squared. Now, we're going to start here with, again, for this video, we want to just look at very in-depth evaluation of the inference techniques for beta 1, which obviously is the slope of our model. Now, what we've got to think about is we've got a larger population, and we take a random sample, and we get the measurements x1, y1, x2, y2, up to xn, yn. We use our sample to create B1, which we sometimes look at as beta 1 hat, which is, of course, our estimate of beta 1. And we've looked at a variety of techniques there. The techniques so far we have been least squares. We also have seen that there's a formula where we can calculate B1, and obviously we can use R or statistical software package or a calculator, and ultimately we're going to see that there's a matrix approach, and that probably will come in. I forget, what is this, video 23? Yeah, this will probably, the matrix approach will probably start at, sorry about that, in probably video, probably 26. That's what's happening. So guys, at the end of the day, we create a B1, which is used to estimate beta 1. Now, some notes here. Because of sampling variation, we know that there's nothing special, nothing holy, nothing unique, if you will. Well, there's unique because it's ours, but because of sampling variation, we could create multiple estimates. Again, the one that we get just happens to be the one that we get from our sample, but our first sample, for example, could create a beta 1 of 10. A second sample, which we usually don't take, but we know it exists, may create a beta 1 of 10.5. And we could do a whole lot of samples. I don't know, we can get really silly here and say our millionth sample may give us a beta 1 equal to 9.2. So guys, anyway, we have a distribution here of B1s. Now granted, in inferential statistics techniques, we ignore all these. We know that they exist, but what we do is we use the one that we collect as ultimately an estimate of the unknown parameter value. But guys, these exist. There is a sampling distribution here for B1 that we'll examine. So we expect our samples to vary. There's nothing holy about our, in this case, B1 being equal to 10. If we took another sample, it could be something different. But nevertheless, we're going to use, obviously, the sample that we have. We usually don't take multiple samples. All right, guys, so let's get a little bit of data here and create this. Let's say, for example, that we see a data set where we collected ACTs on some students and we examined their GPA. And I don't know, let's just create some data here, some numbers. And that'll work. Okay. And let's say the GPA for this student is 2.4. The GPA for this student was a 2.2. Let's say this student had a 2.8. We'll give it a little bit of a linear increasing. I'm not a fan of ACT scores, but here we go. We're going to use an example of that. So guys, let's get out of our blackboard. I've got R up, so I'm going to go ACT. So we have 18, 22, 25, 28, and 32. We should be really, really good at this by now. And we have GPA, which is 24, 22, 28, 20. No, it's not. Doug. 2.4, 2.2, 2.8, 2.9, and 3.5. Okay, the first thing I'd want to do is examine the relationship. Just look at a picture, so I'd look at a plot. And you can see that we do have a positive tendency there. You know, in terms of being on a straight line, you know, this point's a little concerning, but we're going to go ahead and fit a straight line to our model. So what I would want to do here is I would just probably create our model and do a linear model of GPA, function of ACT. And we can see here that we get a B1 of 0.08448. That's pretty cool. That'll be easy to remember. Wasn't such a bad data set after all, right? Now, if I do a summary of our model, you know, we get more information here. So what I'm doing is I'm writing on the blackboard, so over here. So we're going to switch back over to that in just a second, but I don't have this information written down. So guys, our B1 again is 0.08448. And some things, again, what we're going to examine today is we're going to examine this line right here, the one I've highlighted. And you can see what we have here is we have a standard error for our B1 is equal to 0.023. And we end up with a p-value of 0.0349, which came from a test statistic of 3.673 degrees of freedom equal to 3. We can see down here our residual standard error. We studied that in the last video. It's 0.2477. That's the kind of, you know, thought of as the variance of our error. And but anyway, the nature of this this video is to examine this line right here. Where do those numbers come from? What's the mathematics behind it? Kind of, well, you know, everything we do here is a lot like, you know, what we did in our calculus class. We Calc 1, Calc 2, Calc 3. We, you know, we did calculus. We get into analysis and we kind of prove everything. So yeah, that's kind of what we're going to do here. So guys, let's go back to the blackboard, and what you'll see is I've written down. Well, hopefully it'll. There we go. So I've written down the estimates. So what we would conclude here, since, you know, our p-value is less than the typical alpha. Now, if we were setting, for some reason, we needed to control for type 1 error rate, and we set our alpha at 0.01, then we would fail to reject. But right now, we've got, we'll just use the standard 0.05. So p-value less than alpha, we would reject the null. Well, let's go ahead and start looking at the formal test. So guys, the null hypothesis in this assumes, unless there's evidence from our data to indicate otherwise, that the slope of the model is equal to 0. If we get a large enough test statistic, which goes hand in hand with a low p-value, then this gives us evidence against H of O. And if we create this, if we have a large enough test statistic and a low enough p-value, and we get enough evidence against the null, then what we do is we reject the null, and we indicate that based on our data and statistical significance, we feel that the best decision is that the slope of our model is not equal to 0. So guys, what we end up with here is ultimately, we've got our model and we've got our levels. So we've got our y's and we've got our levels x1, x2, however many levels we may have. And so we're assuming you have no idea how hard. I encourage you guys to try that. So we're assuming, unless we can get information from our data to indicate otherwise, that our mean values of y lie on a horizontal line. Now, if we start to get indication otherwise, then we end up concluding our slope is not equal to 0, which of course is indicated by the alternative hypothesis. All right, guys, we're going to get kind of down dirty with this, so it's going to be actually be pretty cool. So, guys, first of all, let's examine just about any test statistic. And what a test statistic is, whether it's a t, a z, a chi-square, is we look at our sample. We look at the claimant or null. And we divide out by the standard error. And again, our test statistics follow some distribution. And so far in this class, we've talked about the normal distribution, z distribution, the t distribution, the chi-square distribution, and the f distribution. So we've got to actually come up with what distribution our test statistic follows in these variety of situations. Well, guys, in our problem here, our test statistic is going to be a function of B1. Our null, of course, is that beta 1 is equal to 0. And our standard error will be the standard error, of course, for B1. And that follows our distribution, guys. We're going to ultimately see that this distribution follows the t distribution with the particular degrees of freedom. Now, next thing we'll want to do, if we go back and, for example, if we do get statistical significance and we reject the null, then we're saying our slope is not 0. Well, that really narrows it down, doesn't it? We're saying that our slope is somewhere from negative infinity to 0 and 0 to positive infinity. Well, there's a whole lot of numbers from negative infinity to 0 and 0 to infinity. So what we'd like to do is we'd like to be able to come in on the real number and actually give us an interval with a particular specified level of probability where we think beta 1 lies based on our estimate of B1. So guys, what we'll do there is we'll ultimately create a confidence interval. In the confidence interval, we'll take our estimate as the center. we will add and subtract margin of error. Guys, from previous confidence interval problems, we have seen that our margin of error can be found by taking our critical value from our distribution times the standard error. And of course, this standard error will be used for B1. Now, I'm just going to go ahead and give you a note here. I know I'll do this. I'm going to try not to do it. But our standard error for B1 is sometimes written as S brackets B1. So these are interchangeable. I'll try my best not to interchange these, but just about bet you anything that I will. All right, guys. Now, I don't really know where I want to go. Let's. I'll tell you what. Let's examine the sampling distribution for B1. Well, previously we know that B1 can be found by taking the sum of the x sub i's minus x bars, y sub I minus y bars divided by x sub I minus x bar quantity squared. And these things come from a normal distribution. And our mean. I'll tell you what, I don't like the way it's setting up. In our mean, it's from the expected value of B1 equal B1, so our mean will be beta 1. And our variance of the normal distribution for B1 is going to be equal to this. Now, I'm not gonna spend much time talking about this. We have an unbiased estimator. We talked about that before. So, but I would like to examine this a little more closely, the variance. And guys, from I think it was assignment number 3, and I believe it's problem number 1. We showed that is equivalent to over this. So the same denominator, but we showed that the numerator, the numerator in the first expression can be equivalently written like this. Now, let's just try to simplify this, and the notation I've always seen for this is just to use k sub I. So if we let k sub I be x sub I minus x bar, over our denominator. Where in the world did that come from? There. Okay. Then, under no stretch of the imagination, we should be able to see that B1 can be expressed more compactly is this. You see this notation. I've got about 5 or 6 books that I refer to when I'm preparing my lectures, and you see this K notation pretty consistent. So guys, a proof of the variance, we can show that the variance of our B1s just by simple substitution. And whoa, that's not true. Forgot kind of an important part there, didn't I? Got sloppy. And we can do some obvious steps here. So we could go, got a case of i's, some of them case of i's. Squared, sigma squared, pull that out. And then look at our y sub i's. And this, of course, is going to be equivalent to that, which will be equivalent to that, which will be equivalent to, let me see, go back to case of O, what did we do here? So case of I squared, so we're going to square those, so that some of that's going to cancel out, so we'll get just 1 over x bar squared. Because when we square the k's, square this over here, so we're going to get squared, so yeah, okay. So, guys, there's just a pretty informal proof of why the variance is what we said it was. All right, guys, let's get into the process of inference. So we'll examine our test statistic. Which will be our beta 1 minus our claim beta 0, and that's going to be 0 the way we've set it up here, over our standard error for B1. It turns out that this test statistic follows the t-distribution of degrees of freedom n minus 2. And you should know by now why we have degrees of freedom n minus 2, because we had to create estimates for beta 1, or well, beta 0 and beta 1. So we had to create 2 estimates for values that we're using in our calculations. So we have to control for that, if you will, and use n minus 2 degrees of freedom. So now, where I want to go from here is really just I'll tell you what. Before we go on, let's. So we got our test statistic, and this will be for our test of hypothesis. And something else I want to show you is our 1 minus alpha confidence interval. And you know what we have here, as I showed you earlier, is our t critical. So we can talk about the distribution now because I've told you that, times the standard error for beta 1. Now let's examine this a lot more. So examine the confidence interval. So if we look at the probability of t of alpha over 2 given n minus 2 degrees of freedom, and we want that less than our test statistic of b1 minus b1 divided by the standard error for b1 to be less than t of course, 1 minus alpha over 2, n minus 2. And of course, we know this is going to give us a value of 1 minus alpha. Now, I want to multiply through by some stuff. But I first want you to recognize that this first part, t of alpha over 2, degrees of freedom n minus 2, will be precisely our negative t of 1 minus alpha over 2 n minus 2. Now that's kind of a weird way to put it, actually, as I'm thinking about it here. You know, we've got this equal. That's the reason I'm wanting to put it in this situation here. Let me. I think that we need to talk about that. All right, guys. So if we got, we know for the t distribution, degrees of freedom, one thing we know is we have a mean equal to 0. So we have symmetry, and we have values to the left of the mean are negative, and to the right of the mean are positive. Now, when we look at this first t of alpha over 2 given some degrees of freedom n minus 2, in a situation where we got alpha equal 0.05, which is typically going to be the case, what this leads to is t of 0.025 for our degrees of freedom. So what we're actually finding here is we're finding the negative t that has area 0.025 to the left. Now, when I actually bring in the notation up here where I have negative t 1 minus alpha over 2 for degrees of freedom, I'm actually taking the negative of this negative to create the positive t with 1 minus alpha over 2. So guys, 1 minus alpha over 2 would be 1 minus 0.025, which would be, of course, 0.975. So it's kind of weird. You would think that the way this is set up, that the negative would indicate the left value, but it actually indicates the right. So now you probably saw that. It's not, I mean, that's not heavy duty stuff, but I want to make sure that you see that. So guys, redoing some stuff. We can, let's see, I need to think about what I'm doing here. If we multiply through by the standard error for beta 1, so multiply the first term, multiply the second term, and use the fact that these two things are equivalent, So we want to multiply by the standard error, subtract beta 1. If we multiply through by -1, okay, so we're going to get beta 1 minus t 1 minus alpha over 2 4 degrees of freedom n minus 2 less than or equal to beta 1 less than or equal to beta 1 plus t 1 minus alpha over 2. Yeah, this is good. Which is still 1 minus alpha. So what we can do here is 1 beta 1 plus or minus t 1 minus alpha degrees of freedom n minus 2 times the standard error for B1. So that's exactly what we end up there. That'd be a classic test question there to show the confidence interval expansion. Don't know if that's what's going to happen or not, so but we'll see. All right, guys, let's go ahead and carry this out. So let's go back to using ACT as a predictor of GPA. All right. So we've collected 5 observations, and we want to generalize now. So we're going to test beta 1 equal to 0, beta 1 not equal to 0. So the slope, if we get a statistically significant slope, it'll just be the change in GPA per 1 unit increase in ACT. So guys, we now know a lot more stuff. So we know our test statistic is going to be 1 minus, beta 1 minus, or B1 minus beta 1 divided by the standard error of beta 1. We know this is going to follow a t-distribution, degrees of freedom n minus 2, which gives us the basis to calculate our p-value and make our calculations for our p-value. Okay, now let's examine this standard error. So the way I want to look at this first is look at it the square of the standard error. So guys, we're going to have from one of the previous lectures, we have the mean square error, the sum of our x sub i's minus x bar squared. As remember, sigma squared is the mean square error. And then this, of course, we can, let's see, we can see that the mean square error is the sum of squares for error divided by n minus 2. So that's the mean square error still divided by x sub I minus x bar quantity squared. And we note the sum of the squares is nothing more than the sum of our error squared over n minus 2 divided by the sum of our x sub i's minus x bar squared. So therefore our standard error for B1 will be the square root. I'm going to cheat here. I don't want to write all that. To be honest with you, I don't have room down here. It's just the square root of this. So that's going to be the first thing we want to do in our calculations, is go ahead and come up with those parts. So the parts that we're going to need here is I want to come up with the sum of the errors squared. I want to come up with n minus 2. Ooh, that's a tough one. And we want to come up with our sum of the that's right. So yeah. All right, guys. I'm going to jump back over into R. If you're not a fan of R, sorry, but if you would rather do this with your calculator, I'm perfectly fine with that, using just manipulations of list 1, list 2, list 3. So guys, I got my model, so I can come up with my residuals of the model, and clearly I can residuals of our model quantity squared. And of course, that's not what I want to do. I want to sum up the residuals of the model squared. So when I get that, my sum of my E sub i's is going to be 0.184069. N minus 2, that's a really easy one. And the next thing we want to do is calculate our sum of our x sub i's minus x sub bar. So what I would need to do here is I want to sum up my x sub i's, which I called those ACT, minus the mean of ACT. And I actually want to take those and square them. I tell you what, I'm going to play this safe. I want to call my differences. So I'm going to, I think I was going to be okay there, but I don't want to take that chance. So let's just take the ACTs minus the mean ACTs, and let's go differences squared. So we'll sum differences squared. And we get the sum of our x sub i's minus x bars squared. We get a summation of 116. So guys, putting everything together, we need to take our point 184,069 divided by 3. Divided by 116, and we get 528. So what's going on here? So our sum of our errors squared Well, this is always fun. So let's do our residuals again. So if I take let's do our residuals, our model, and let's do a residual squared. And let's do sum of resid squared, 0.184069. That's what we want. We did have a data 5 entries, right? Yeah. And let's check the other. So we need to set which one of those? 116.18469 divided by 3 divided by 116. That's what's going on here. Okay. .02. Okay. So and I got a little ahead of myself there because what we calculated there was the standard error squared, and of course we had to take the square root of that to get our standard error. So guys, you can see now that 0.022998 is precisely what we started out with there. So I'm going to use that as 0.023 is the standard error for B1. I'm actually writing this. All right, guys, let's go back to the blackboard so we can see that we've got this. So first thing I want to do is calculate our test statistic. And our beta was 0.08448. Divided by standard error, which is 0.023. And I'm going to use this all right, I'm just going to use my calculator for this. So 0.08448 divided by 0.023. So we get a test statistic of positive 3.673. All right, so this tells us that our sample estimate, B1, is 3.673 standard errors, above the claim that the beta 1 is equal to 0. So it appears from here that we are going to reject the null. So now we got to calculate our p-value. So guys, ultimately what we get here, it's been a while, but remember we conducted a not equal to, so we need to find the area in the curve, the area under the curve, to the right of 3.673, and we need to find the area under the curve to the left of negative 6.73. So guys, going to jump back into R. Remember how to find, for a t-distribution, we use P of t. And what I can do there is put in negative 3.673, degrees of freedom 3, and multiply this by 2. And I get my p-value of 0.034927. Now we're going to be off a little bit. Well, okay, it's fair enough up here where I'm highlighting. Rounded to 4 places, we get the same value. All right, guys. So clearly we reject the null, so we have evidence to support. That evidence from our sample is more supportive of this statement than the null. So B1 not equal to 0, again, tells us a lot, but we want to know more information. Just where on a specified level of probability is B1. So guys, we're going to do a 95% confidence interval here, which would be standard with alpha 0.05. So guys, again, we have beta 1 plus or minus our T critical, 4 degrees of freedom 3, times the standard error for B1. So guys, we know our B1, 0.08448. Plus or minus our T critical, we'll go get that in just a second, times our standard error. That was, I'm thinking Michael Jordan for some reason, yeah, 23, times 0.023. Now what we need to do here is we need to find in the T distribution, we need to find the T criticals that encompass the middle 95% of our distribution. So guys, we just need to find what has 0.025 to the left of it. That'll give us our negative, and obviously because of symmetry, that'll give us our positive. So guys, back to R. Hopefully you haven't forgotten that we do that with QT. We want 0.025 to the left, degrees of freedom 3. So we're going to have 3.182 is our 3.182446. So you can see I've already written that there. So guys, I'm going to use the calculator here just to do the calculations. And the 95% confidence interval that I get goes from 0.011. You can see that we really just kind of sneaked in statistical significance to 0.158. So what we can say here, there's a 0.95 probability this interval contains B1. There's not a 0.95 probability that beta 1 is contained in that. Because guys, we don't know beta 1. It's unknown. So we can only express our confidence interval interpretation on the confidence interval. So again, there's a 0.95 probability this interval contains B1, beta 1, I'm sorry. It definitely contains B1 because we used B1 as the center of our calculations. But there's a 0.95 probability this interval contains beta 1. Again, I'm going to stress this. It is not appropriate to say there's a 0.95 probability that beta 1 is contained in our interval. We don't know beta 1. We've got that interval. We can specify a probability based on it, but we can't specify a probability based on something we don't know. And beta 1 will always be unknown. That I think concludes. I'll tell you what, if I've got some extra time, I got something else I want to do. 52, we're good. All right, guys, let's let this be the end video, I think number 23.